this stuff has fallen apart into these individual molecules. So maybe the right way to look at this whole problem is, why is that N-N bond so weak? There's another class, and there's a few other molecules that work like this that you can go down and get out of the stock room. They're that stable. Most of the molecules that are like this are very chemically reactive. Now there's another way in which you can put together a molecule in a way that violates the octet rule. And in this case, we say that the central atom has an expanded octet. Well, expanded octet, that just means more than 8 electrons around that central atom. And the example in this case is going to be sulfur hexafluoride, SF6. This molecule, there's a huge amount of studies done on sulfur hexafluoride, and one of the main reasons is that there is a very similar compound, which is uranium hexafluoride. And, you know, everybody's interested in uranium compounds. Uranium hexafluoride is used in the production of nuclear weapons and in nuclear fuels. And this is a molecule which is very similar to uranium hexafluoride, but isn't radioactive and doesn't blow up, and the IAEA doesn't mind if you have a lot of it. It's got some other uses also. Anyway, so you can figure out how many electrons there are going to be in this molecule. Remember, the fluorine is one of the halogens, so it's got 7 valence electrons, and there's 6 of those guys. So that's 42 electrons coming from the fluorines alone. And then the sulfur, which is right underneath oxygen in the so-called chalcogens, right here, comes in with the same number of valence electrons as oxygen does. That's 6. You get a total of 48 electrons. And the only way you can draw a structure so that the sulfur is in the middle, and we know that it is going to be one in which there are, let's make sure we can count them up, 2, 4, 6, 8, 10, 12 electrons around the sulfur atom. That can only happen, you know, that's kind of a crowded arrangement compared to the octet, right? So that's only going to be able to happen when the electrons are spread out, when the bonding electrons in this case are spread out around a relatively large atom. So this kind of thing happens mostly when you're working with atoms, central atoms, which are down in here. Okay, so below, certainly, n equal the second row, which is where n is equal to 2 for the principal quantum number. So I'm afraid that the way we state this rule, it makes it sound like that the octet rule doesn't work for very many compounds, and that may not be totally wrong. Here's the place where the octet rule is going to work great: organic chemistry. So if all you're interested in is carbon compounds and drugs and plastics and stuff like that, and you're interested in studying that next year, the octet rule works great for all kinds of organic compounds that contain carbon, hydrogen, oxygen, and nitrogen, and that's almost all of them. Okay, that's the end of our discussion of Lewis dot structures. Are there any questions about that? Great. Let's go on to the next topic, which is in a weird spot here. So now what we want to talk about is the strengths of chemical bonds. So first of all, you got to know what a chemical bond is, right? That is when I've got 2 atoms in a molecule close to each other, and usually it's accompanied by an increase in the electron density between the 2 atoms on the line between the nuclei that are supposed to be involved in the bond. So, for instance, in the case of that sulfur hexafluoride, you notice that the sulfur was bound to all of the fluorines. All of the fluorines were bound to the sulfur, but none of the fluorines were bound to any of the other fluorines. Okay? So some atoms in a molecule are bound to some other atoms, but not necessarily to everything else in the molecule. And that little distinction is important to keep in mind when we're thinking about these bond strengths. So the enthalpy associated with the strength of a bond is the amount of enthalpy that you have to put into a molecule with that bond in order to completely break it apart into fragments. All right, I'll show you several examples. I want to make sure, I'm not sure how much you guys got a chance to talk about enthalpy, E-N-T-H-A-L-P-Y. It's not exactly the same as energy. It's kind of related to that. It's equal, as it turns out, to the amount of heat involved in a change as long as you're carrying that process out at constant pressure. Okay, so roughly speaking, you can think about enthalpy as heat. It's not always, but often. And you can think about it as kind of like energy. And if you want to know all the details where we keep all of this stuff straight, then keep going, take our thermodynamics course. We spend about a month talking about this thing. Okay, so we want to be a little more specific. I'm going to take a bunch of molecules, let's use a mole of the molecules, and I'm going to break the bond in every one of that mole of molecules. How many molecules in a mole, do you remember? Avogadro's constant. Do you remember what Avogadro's constant equals?
0.022 times 10 to the 23.
Good. So it's a lot of them, okay? So we're going to put in enough energy to break a lot of those guys' bonds. And we got a lot of those molecules. Now, I don't want everything to get confused. I'm only interested in breaking the bonds between two atoms within a molecule. But you know that if you bring two molecules real close to each other, they start interacting, and maybe they form a liquid or maybe they form a solid. There must be some amount of enthalpy associated with that, which there is. So we don't want to have to worry about that, so we're only going to be talking about gaseous molecules, gas phase molecules at the moment. All right, so here's an example. H2, in the gas phase, that's hydrogen. I can break that apart into just hydrogen atoms in the gas phase. By the way, this happens all the time. There is nothing unusual about having free atoms of hydrogen flying around completely on their own. They're very reactive, okay? But you only get a reaction if you run into something else. So the whole trick is just to keep these atoms from running into anybody else with whom they might form a bond. So in this case, it turns out that to break apart a whole mole of these hydrogen molecules, I have to put in 436.4 kilojoules of energy in order to do that. Now, if I start with 1 mole of hydrogen molecules, how many moles of hydrogen atoms do I end up with?
1.
1? Well, how many atoms come out of every molecule? Look at the reaction, it tells you.
2.
2. So if I had a dozen molecules, how many atoms would I end up with? 2. If I start with 12 of them, I'm going to end up with 2 atoms. 12 molecules. 12 molecules makes 6 atoms. 1 molecule, you said, makes 2 atoms. Yeah, well, forget these guys. You can't pay attention to anybody else. This is science. Okay, so you guys shut up. So 1 molecule makes 2 atoms. 3 molecules make how many atoms?
6.
Good. 12 molecules make how many atoms?
4.
A mole of molecules makes how many atoms?
1. Wait, one more. Oh, use the Avogadro's number, so it's...
No, you don't have to tell me the number. Just tell me how many moles. I mean, not the number of atoms, the moles of atoms. Let's try a dozen molecules. How many molecules in a dozen molecules?
12.
Good. How many atoms do I get out of a dozen molecules?
12. So it doesn't say.
Wait a minute, let's back up again. 1 molecule gave me how many atoms? 2. 2 molecules gave me how many atoms? No, that's not what you said before. If 1 molecule gives me 2 atoms, then 2 molecules must give me
2 atoms.
not 2 atoms.
4.
4 atoms. 3 molecules is going to give me how many atoms?
6,
4 molecules is going to give me
8,
5 molecules is going to give me 8 molecules is going to give me
16,
12 molecules is going to give me
24,
24. Okay, 12 molecules is a dozen. How many dozen atoms is 24 atoms? 2. So 1 dozen molecules gives me how many dozens of atoms?
1,
Let's back up again. How many molecules in a dozen? 12. How many atoms do I get out of 12 molecules? You said this correctly before. That's the only reason I'm going back.
on the spot.
I know you are on the spot. That's life. So just put the concerns aside and see, I know you know it because you've answered correctly already several times. But you're letting yourself get confused and then you start answering off the top of your head or something. So let's back up. We'll start again with 1 molecule. 1 molecule makes how many atoms? 2 molecules makes 4. 3 molecules makes 6 molecules makes 12 molecules makes
24,
wait a minute. So remember that. 12 molecules makes how many atoms? 24. How many dozen is 12? 1. Right. So 1 dozen molecules makes how many dozens of atoms?
Say it again. 1 dozen.
1 dozen molecules makes how many dozen atoms?
24.
You said 24 atoms. How many dozens is that?
2.
So 1 dozen molecules makes how many dozens of atoms?
2.
Good. 1 mole of molecules makes how many moles of atoms?
1 mole.
Uh-huh.
1 mole.
Ooh, what's the connection between moles and atoms? I'm so glad you asked that. What's the definition of a mole?
1 mole is 6.022 atoms.
No.
Times 10 to the 23rd.
No. What's the definition of a mole?
6.022 times 10 to the
23 months.
Times 10 to the 23. Yeah, you know what? We really don't care what that number is. Let's call it n sub a. It's 6 times 10 to the 23rd what? No. No. What's mole mean? Okay, let me ask you this. Almost, we're getting closer. So let me ask you this. What's a dozen? 12 what? 12 of anything, whatever you ask. So if I say, no, that's very good. So a dozen eggs, that means 12 eggs. What if I had a dozen cartons of eggs and each carton had 12? Then you'd have 144 eggs. You wouldn't have 12 eggs, right? Okay, a mole is just like a dozen. So it's not 6 times 10 to the 23rd atoms. It's not 6 times 10 to the 23rd molecules. It's not 6 times 10 to the 23rd paper clips. It's 6 times 10 to the 23rd of whatever. And you got to tell me what the whatever is. Just like if I say a dozen, you don't know whether I'm talking about a dozen eggs or a dozen pencils or a dozen molecules or a dozen atoms or a dozen of anything else. A dozen is just 12 of whatever you're interested in. Moles works exactly the same way. So you can see this is important to know. So now I'm going to come over here and work on you guys. So 1 molecule of hydrogen makes how many atoms? 1 molecule makes how many atoms?
1 molecule of that? Right?
Of H2. Uh-huh.
1 mole of H2. Wait, can you repeat? I'm sorry.
1.
I don't want to get picked on.
That's good. I'm not trying to pick on you. I
I
just,
get really nervous.
that's fine. We all get nervous. Look, I'm sweating, and I'm talking to a dozen people at once.
Oh, no, it's not dozen.
So listen to the question.
Okay.
One molecule
Okay.
of hydrogen, which is on the left-hand side of this reaction, makes how many atoms of hydrogen? Two, I agree. Two molecules of hydrogen makes how many atoms of hydrogen?
One. Four.
Four. How did you get four?
Because one molecule is like one atom is two molecules.
No. The other way around. Listen to what you're saying.
Yeah, one molecule is two atoms,
Uh-huh.
and two molecules is four.
Because 2 times 2 is 4, right? Okay, and if I had 3 molecules, how many? 6. How'd you get 6 so quick?
3 times 2.
Very good. And if I had a dozen molecules,
It's 24
24 what?
atoms.
Atoms. And how many dozens of atoms is that?
2.
2. In fact, you could have saved yourself a lot of trouble by saying 1 dozen of molecules makes 2 dozen of atoms. You just multiply 1 by 2. And if I had 1 mole of molecules, how many moles of atoms am I going to end up with? 12. Let's back up again.
Okay, 1 mole of
1 dozen molecules makes how many dozen atoms?
24. Okay, one dozen of molecules, how many atoms?
No. 1 dozen molecules makes how many dozen atoms?
Oh, it's 1. So one.
I guess maybe I should give up. Okay, so remember I said dozens works just like moles. So everywhere you hear the word dozens, you put in the word moles. So if 1 dozen of molecules makes 2 dozen of atoms, 1 mole of molecules must make 2 moles of atoms. You hear what I did there? I took the word dozen and crossed it out and put the word mole in. Are you okay with that? Okay. All right. So this is 436.4 kilojoules for every mole of molecules. For chlorine, it's a lot smaller, 242.7 kilojoules. That's because the chlorine-chlorine bond, that's a single bond between 2 chlorine atoms, is much weaker than the bond between 2 hydrogen atoms, okay? In the case of hydrogen chloride, and here I'm not talking about hydrochloric acid. Hydrochloric acid is what happens when HCl goes into water. This is gas phase hydrogen chloride. You can go down and get this in the stockroom, making a gas phase hydrogen atom and a chlorine atom also in the gas phase. And you see, that's kind of close to the H2. This is a bond which is very similar to the one in H2. O2, that's much bigger than the one in any of these ones that we've seen before, and that is because we say there are 4 electrons being shared between the 2 oxygen atoms in the O2 molecule. It's a kind of weak double bond. In the case of nitrogen, this is the strongest bond of any homonuclear diatomic molecule. That's a molecule with 2 nuclei that are the same, 2 atoms that are the same, 941.4 kilojoules, almost a megajoule per mole. That's enormous, and that, we say, is supposed to be because each nitrogen atom is sharing 6 electrons with the other nitrogen atom. So this is a triple bond. You see, our picture is supposed to be that a single bond is a single covalent bond is sharing 2 electrons, a double covalent bond is sharing 4 electrons, a triple covalent bond is sharing 6 electrons. You take the number of shared electrons, divide by 2, that tells you the bond order, the order of the bond. And in general, single bonds are weaker than double bonds, and those are weaker than triple bonds. These guys are a little out of order. All right, so here's a big pile of experimental information about these bond strengths. Some of them, there's only one molecule that has this kind of bond, so you just measure it and you know it really precisely. Those are the ones that are in red, so HH, HF, HCl, HBr, HI, iodine, bromine, chlorine, fluorine, oxygen, nitrogen. Are those the only ones they have up here? Yes. And you can see that, the story I told you is kind of roughly consistent here. The single bonds are the weakest ones. Oxygen actually has a relatively weak double bond. You can tell that by comparing to the CS double bond or the CO double bond here. That's 745. That's a lot more than this, which is about 500. And these halogen bonds are relatively weak. Okay, so one of the reasons we're interested in bond enthalpies is because if you know the bond strengths, then you can figure out the amount of heat which is given off in a reaction. That's going to be closely related to the energy changes that are going on in a reaction, and that'll tell you which one's a good fuel because it generates a lot of heat when you burn it up. That's a chemical reaction, right? Or which one is going to be more stable because you get more energy out when you produce it. So all of the chemical reactions that you're going to see can be thought of. They aren't actually occurring this way because this is really the hard way to do it. But you could imagine that you take all of the reactant molecules, that's everything written on the left-hand side, and blast it to atoms. You atomize it, okay? Then, and so you know and you can figure out the total enthalpy to atomize everything by adding up the strengths of all the bonds that you have to break. Then you form the products. And when you form those, energy comes out, the amount of energy that is given off when the bonds are formed. So if you know the bond strengths for everything in the reactants and everything in the products, then you can figure out what the difference in the energy is between the reactants and the products. And that's what this equation up here tells you. Delta H with that little superscript thing on the right-hand side that looks like a 0, or sometimes it's a degree marker, and sometimes it's got a little horizontal bar in it. You read that as standard, and later on we'll explain to you exactly what standard means in this case. So the delta H standard for a reaction can be calculated in the way that's described here. If delta H standard is positive, wow, that's backwards. Sorry. Which is the energy of the products minus the energy of the reactants, then we say that the reaction is endothermic. Endo means goes up or goes in, and thermic means heat. If it's the other way around, then that means that when the reaction happens, the reaction is exothermic, heat comes out. Okay, so let's use this to figure out about a apparently relatively simple reaction. This is the reaction between hydrogen molecules and fluorine molecules. And let's see, I know I've got 2 hydrogen atoms in my 1 hydrogen molecule, and I've got 2 fluorine atoms in my 1 fluorine molecule. So when I break the hydrogen-hydrogen bond and break the fluorine-fluorine bond, the only new kinds of bonds I can make will be between hydrogen atoms and fluorine atoms. And because I got 2 hydrogen atoms, I must be able to make 2 hydrogen fluoride molecules. And this is another molecule kind of like HCl. If it's in the gas phase, we call it hydrogen fluoride. It's a perfectly well-known, well-understood molecule. If you dissolve it in water, it becomes hydrofluoric acid, very scary material, which with any luck you'll never have to work with. Okay, so here's the story. Now we can put in some numbers and figure out the enthalpy change associated with this reaction. So I've got one molecule of H2 on the left-hand side. That's a reactant. I'm just breaking the one bond there. And I know from that table I just looked at that that takes 436.4 kilojoules to do that with a mole of hydrogen molecules. I have to do the same thing for the other reactant. That's fluorine. I'm only breaking one bond. The fluorine single bond is one of the weakest bonds among homonuclear diatomics. It's only about 157 kilojoules per mole. Okay, now that's the reactants, and so the total amount of enthalpy I have to put in order to blast everything to atoms is going to be the sum of those two. Let's see, it's about 160 plus 440, that's 600, right? About 600 kilojoules per mole. How much do I get back out? Well, every time I form one of these hydrogen fluoride molecules, I get out the strength of the hydrogen fluoride bond, which is 568.2 kilojoules. I got two of these molecules, or 2 moles of these molecules, and so 2 times this is about 1136. So I'm clearly going to get out a lot more enthalpy than I put in. And if you go through and do the arithmetic, you'll see that you get 543.1, it's very precise, kilojoules per mole coming out of this reaction. Is this exothermic or endothermic? This is exothermic, that's right. It's a pretty big exothermicity, by the way. You can use this to make a laser, and there's a whole bunch of stuff. People are going to use this, sorry, I have to keep bringing it up, as a weapon. Because it puts out a huge amount of energy, and you know, if you can atomize that stuff, I guess you can atomize the enemy. Okay, here's another one, but this is a slightly different story. So here's one of my favorite reactions. 2H2 in the gas phase plus O2 in the gas phase yields 2H2O in the gas phase. What's H2O called usually? Water, good. So when we have a reaction like this, in which I'm adding oxygen to something, what do you call that kind of a reaction? When I add oxygen to something. Combustion, exactly. So this is burning hydrogen, okay? I mean, you already got a clue. This is going to be exothermic, right? Because you know that when you burn things, they give off heat. Okay. The enthalpy change for this reaction, is 483.6 kilojoules per mole. You know the bond enthalpies for hydrogen, for H2, from our table, and you know the one for O2, also from our table. Oops, okay. Now I have to go over to my other slide, which has the final answers. Now, we want to keep going with our original idea, which is that you blast all of the reactants and all of the products into atoms. When you blast water into atoms, it goes in 2 parts. First, you take off one hydrogen atom. Okay, so I'm removing a hydrogen atom from a water molecule. But to get the second hydrogen atom off, I'm not taking it off a water molecule anymore. I'm taking it from a bare oxygen atom. These are both well-known chemical reactions that you can have happen in the laboratory, one after the other. Okay? But I hope it seems reasonable to you that these 2 processes are different in energy, because I'm starting with different stuff and I'm ending with different stuff. It's just that in both cases, I'm taking out a hydrogen atom. And you can, so as I say, these have both been measured. The energy for each one of these, one of them, let's see, the first one is 502 kilojoules per mole. And for the second one, it's 427 kilojoules per mole. See, it's easier to break off this hydrogen than it is to take off the first hydrogen. So the total amount of enthalpy it takes to break these guys apart, to take a water molecule and break it into an oxygen atom and 2 free hydrogen atoms, is the sum of these two, 929 kilojoules per mole. Okay, and now you can see what's going on. First, you're going to break 2 hydrogen bonds. Then you're going to break an oxygen bond. So you have to put in a lot of energy to do that. Let's see, I got 436.5 times 2. That's 873 kilojoules per mole to break up the hydrogens. I'm going to add to that the 499 kilojoules per mole for breaking up the oxygens. And that's going to give me 1372 kilojoules per mole. Okay? And then there's only 929 kilojoules per mole for every water molecule. So the total, but I'm forming 2 water molecules. So I'm going to multiply this guy by 2, and you get 1858. So I put in 1372. I got 1858 coming back out, so my net difference is 486 kilojoules per mole. That's how exothermic this reaction is. That's a lot, okay? We're going to go until 10 minutes of. All right. That's the end of what we were going to say about that. Are there any questions about that? No. Good. All right. Now that we have a way, so now we're on to chapter 10, I believe. Now that we have a way to start thinking about how strong a bond is, and I hope you're convinced, at least temporarily, that the strength of a bond is a worthwhile thing to know when you're thinking about chemical reactions going on and the structures of molecules, then we can start thinking about what determines the strength of a bond. When do molecules give off a lot of energy when they, say, burn up or when they undergo some other kind of reaction, and when do they not give off very much energy? And that turns out to be related to the way in which the atoms are arranged inside of the molecule. We call that the molecular structure, okay? This was the subject of a big argument that went on for several centuries, and so we've all come to finally to an agreement that molecules actually are made of little pieces. This is all stuff you've already heard. Little pieces called atoms, and the atoms are arranged in a more or less permanent, rigid arrangement in space. That's the structure of the molecule. And this arrangement of the atoms in space and the strengths of the chemical bonds determines everything about the molecule. All of its chemical properties, all of its physical properties. If you know the structure of a molecule, you know everything there is possibly to know about it. So we need a way we have some simple stories which you can use to begin to think about the arrangement of atoms in molecules, the structures of these atoms. And the simplest theory is usually called VSEPR, or sometimes people kind of move the letters around and it becomes Vesper, like the character in that James Bond movie. So it stands for valence shell electron pair repulsion. Okay, so that's supposed to be a summary of the physical picture you can have in your mind about what's going on. And we only have time to do the first one. So, and it has its own special notation, by the way. So if you've got an atom, A, which is bound to 2 other atoms, they're identical, so they're called B. So I've got a molecule with the formula AB2, okay? we're going to pretend for the moment that the A atom is the one in the middle of the molecule. It's not always that way, but it often is. In that case, how many atoms are stuck onto atom A? 2, because that's all there is left, right? Now, you have to draw a Lewis dot diagram for this molecule, and if you can do that, you'll be able to see that, for instance, in this case, there may be no electrons left over on the central atom, electrons which are not involved in some kind of bonding pair. A good example of this molecule, a molecule like this, by the way, will be carbon dioxide, CO2, right? That's a molecule that's on the front page of the newspaper every once in a while. Okay, so we say there's no lone pairs on the central atom. In that case, you can kind of think about things this way. All of the electrons are either hanging out between one of the B atoms and the central A atom, or they're hanging out between the central A atom and the other B atom. And according to valence shell electron pair repulsion, they push each other apart as far as they can go. There's only one geometrical arrangement which gets these two sets of valence shell electrons as far apart from each other as possible, and that's to have them all in a straight line, okay? To have the atoms, the nuclei, all in a straight line. In that case, the angle between the bond on this side and the bond on this side is 180 degrees. The molecule has all of the nuclei, the 3 of them, laying on a straight line. So we say the structure is linear and the geometry is linear. And you're going to use the same principle to figure out the structure based on how many sets of valence shell electron pairs you have to worry about. And that'll be the topic, probably, of the next lecture. So thanks for coming by, and good luck on the rest of the class.